Greetings and salutations. Today we're going to be talking about 6.5, which is going to cover using synthetic division to start factoring. And we are going to learn about the rational root theorem. And we're going to also cover some just kind of different factoring scenarios. So let's get rolling right away. We're going to use factoring now to solve. So we're going to be solving polynomial equations. And so this first one here, we have a trinomial. It's a fifth degree trinomial, and you should always look right off the bat to factor out a common term. So I can factor out a common factor of 3x cubed out of each one of these terms. So I factor a 3x cubed out, and what I have left now is x squared plus 6x plus 9. And so I start factoring it like that. The stuff that's remaining is a quadratic trinomial, so you should be familiar with unfoiling those. So we will unfoil that stuff, and what we end up with here is 3x cubed times x plus 3 times x plus 3. So for the solution to that, what makes 3x cubed 0? See, we don't put parentheses around this typically, but some people I think just like having them. So what makes that factor 0? 3x cubed, that would be 0. So x equals 0 is a solution. And then what makes x plus 3 0? They're the same factor, actually would be negative 3. Good. Okay. So a couple different solutions there. In the next example, B, we have, well, first of all, it's not set equal to 0, so let's set it equal to 0. And then we actually just talked about this. You can unfoil trinomials that have an even degree with a middle term that's half the degree, and the final term is constant, right? So this actually unfoils. So you can factor this as x squared and x squared, and two factors of 36 that add up to negative 13 are minus 9 and minus 4. Haha, look at what happens there. That's a double difference of squares.
Yes.
Yes, so this is going to get a little fun. We're going to go a little crazy here. X squared minus 9, that's x plus 3 times x minus 3. And x squared minus 4, that's a different squares, x plus 2x minus 2. Haha. I keep saying that. Haha. So what are the solutions here? Plus or minus 3. I'll use a plus or minus. Or plus or minus 2. Yeah? Okay, so those are kind of just some different scenarios you might run into when you're factoring. All right, let's move on to the next one. The next one here has 4 terms. So if it has 4 terms, you can't see this, but on the whiteboard to the left of me, we kind of have all of our different types of things we factor. And so with 4 terms, one of the strategies we have is factor by grouping. So let's just take a peek and see if this groups. So group the first 2, the last 2. Okay, group that. I go x squared out of there. I'm left with x minus 9. Take a 27 out of there. I'm left with x minus 1. Does that group? That doesn't group because these two things are not the same. So it kind of looked like it might group, but it doesn't group. So I'm going to make a little new acronym and say DNG USD. You know what that stands for? Does not group. Use synthetic division. Good. All right. So does not group, use synthetic division. So we are going to use synthetic division to factor this one. So I'll put my coefficients in there. And now the weird thing here is what am I going to put in the box? Like, how do I know what to try for a factor? Okay, so we're kind of getting a little bit ahead of ourselves here, but one way, probably the best way to do this is to look at a picture. And so you have graphing calculator. You might actually have a graphing calculator. You might have the app on your iPad. But I graphed this on the Inspire. And when I graphed it, this is the graph, what the graph looks like. And so it looks like we have one root at 3. Okay, so I'm going to go back then and I'm going to use 3. 1 root at 3 and see if that works. Okay, so put 3 in the box. I get 1. 3 times 1 is 3. Add them, you get negative 6, negative 18, 9, 27, 0. Hey, we got a remainder of 0. Look what we got there. There we go. Let's go. Let's go! All right, so we got 9 as a constant, x term is negative 6, and the quadratic is a 1. So what we just determined there, Aaron, is that 3 was a root, so x minus 3 was the factor that we essentially divided by, right? I know you said negative 3, and I think that's what you're thinking. So look at what we have left here. We have this little quadratic trinomial, and when you get it down to a quadratic that's left, you can just unfoil that, and if it doesn't unfoil, then you can DNFUQF that. Does not factor, use quadratic formula. Okay, so this actually factors. This is x plus, sorry, not x plus 3. It's x minus 3 times x minus 3. And so this polynomial actually was a perfect cube. It was x minus 3 cubed. I'll just write it all up. X minus 3 times x minus 3 times x minus 3. And so the solution is x equals 3. All right? I have the solution up there. What do you mean? Like that's the one I saw on the graph and I picked, right? So, yeah, that's what I used to factor it, right? And I factored it and I found that there was more x minus 3 factors, so that was the only solution. Okay, so like we're just going to keep on going down the page here. I clipped this out of the book. This leads us to talk about multiplicities. So just have a look at this from the book. So sometimes a polynomial equation has a factor that appears more than once. This creates a multiple root. In the example, 3x to the 5th plus 18x to the 4th, this is the first one we did. 0 has 2 multiple roots. And, wait a minute. Yeah, 0 has 2 multiple roots, 0 and negative 3. So for example, the root 0 has a factor 3 times. And let's just go back to that problem. We did that problem, right? So this problem right here, we ended up doing this, factoring this, and we factored out a common term of 3x cubed. So if I expanded that, that would look like this. 3 times x times x times x, right? And so 0 ends up being a root essentially 3 times. So what we would say on that is that we would say 0 has a multiplicity of 3. Move that over. Well, yeah, that's fine. And 3 has a negative 3 has a multiplicity of, it shows up x plus 3, x plus 3. So this has a multiplicity of 2. All right, so like if the root's repeated, you'd say, oh, that has a multiplicity of however many times it was repeated. Okay, so what's the point of all that? Well, when it has an even or odd multiplicity, that implies something on the graph. So if you read about this, it says if it has an even multiplicity, that at that root or that x-intercept, it goes up and it does not pass through the axis and it bounces back, kind of like a parabola does. You know how a parabola goes up and then it has like a maximum or minimum and then it comes back down. So if a multiplicity has a root has an even multiplicity, it bounces back at the axis. If the root has an odd multiplicity, like in this case 0 had an odd multiplicity, the one we were just talking about, the graph goes up to the root and it bends and goes through. Doesn't that look familiar? How it kind of bends like that and goes through? Yeah, that's kind of the x cubed looking graph, isn't it? Okay, and so that's what happens when it has an odd multiplicity of 3 or 5 or 7, is it's going to bend and then it's going to go through the axis, so it actually passes through. Yeah.
Could you ever have an x in the box for synthetic division, like 3x?
Not for what we're doing. I don't know. I mean, maybe for something like, I don't know. It's a good question. The question was could we have an x in the box for synthetic division? But I mean, I guess it just depends what you're using it for. Maybe. I don't know. I've never done it. I don't want to say no, because maybe you could, you know? Okay, so that's a little bit about multiplicities there. And if we go up to the problem that we just did, right, this would be 3 is the only root, but then we would say that that has a multiplicity of 3. Because it happens 1, 2, 3 times. Okay? So if I was graphing that and go back to the graph that I graphed on the TI Inspire, you'll see that that bends, right? It bends and goes through at that value 3. Okay? All right, so let's try some more, and these are going to be more factoring using synthetic division. Because look at here, we have a 4th degree polynomial with 5 terms. All right, well, we can't unfoil that. There's no common factors to factor out. You know, it's not factored by grouping, so we're going to use synthetic division. So let's set up synthetic division, and I don't think there's any terms missing. We got 1, -8, 24, -32, and 16. How are we going to know what to put in the box here?
Put in the graph.
Well, you can look at a graph, right, and determine. But there is another way if you don't have a graph. And this is called the rational root theorem. So I'm going to jump a page ahead. The rational root theorem states that if you have a polynomial, integer coefficients, every possible rational root of the polynomial equation can be written in the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So, you know, that reads like a typical math book. What does that mean, right? So what does that mean for our equation? So we're doing x to the 4th minus 8x cubed plus 24x squared, blah, 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 blah. Which one is the constant term?
16.
16, so that is your p. Which one is the leading coefficient? 1, that's the first term's coefficient, 1. So that is what we determine is our q. All right? So what the rational root theorem is saying is all of the possible factors are plus or minus factors of p over plus or minus factors of q. All right, so what are all the factors of p? I think it was 16, right? So all the factors of 16 are 1, 2, 4, 8, or 16. And all the factors of q are just plus or minus 1. So this rational root theorem says if, like, for your rational roots, they have to be plus or minus p over q, where p is a factor of the leading or the constant term and q is a factor of the leading coefficient. So the only possible factors that we have here are going to be plus or minus 1, 2, 4, 8, or 16, right? It even would be way uglier if q was a number not equal to 1, because then you would have fractions. So the other alternative is just simply guess and check. It's you guess what value is a root, and you would just put those values in the box. So you'd say, oh, I don't know, I'm going to guess and check, and then you'd just maybe start with the lowest number, 1, and work your way on up. I don't know. I'd probably start with positive 1. It's a little easier. You might get lucky and get 1. Because once you find 1, then it chips it down to a cubic, and it might factor by grouping, or if it chips it down to a quadratic, you can unfoil it. All right, so that's the other alternative. I think we're going to test you on one question where you have to do that, but there's not a ton of factors. And I would just start with 1 and work your way up. But in this case, I graphed this one, and I have here the graph, which turns out to have a root of 2. And it looks like it's the only root. Okay, so 1 would not have given you a remainder of 0, correct? Yep. So let's try 2 and see where it gets. And this one, doesn't this look kind of funny? Like, it doesn't look like a typical vertex, right? It bounces, but it doesn't look like a typical, like, kind of a minimum, doesn't it? And doesn't it kind of like go down and it's like, whoa, and then it like kind of hangs out like really close to the axis and then comes back up. So maybe there's something weird going on with this one. Does anyone have any guesses?
2.
Huh?
2.
2? Oh yeah, 2 in the box. Yeah, good. So let's try 2. All right. So let's put a 2 in there. And so we got 1. 2 times 1 is 2. Negative 6, negative 12, positive 12, 24, negative 8. Okay, it works. All right, so we determined that x minus 2 is a factor. And what I have left is this leftover stuff here, right? This would be x cubed minus 6x squared plus 12x minus 8. And maybe we could graph that by grouping. Graph it. We could factor it by grouping maybe. But we can't. Darn. So we have to use synthetic division again for the leftover stuff. So use synthetic division again. The only one that seemed to work was 2. So let's try it again and see if it has a multiplicity greater than 1. So 1, negative 6, 12, negative 8. Synthetic division rocks. I love synthetic division. See, someone could clip that out and then make like a funny thing and embarrass me about it. Wait a minute. What's going on? Now it's embarrassing because I screwed something up.
You used a 2 instead of a 1 at the beginning.
Aha! Purposeful mistake. I do that to see if you're paying attention. Good job, Dave. You win an award.
What award?
Phineas and Ferb stickers from the internet. All right, so 1 there. Good catch. 2 times 1 is... Uh-oh, we got some crusty wrong answers there. All right, 2 times 1 is 2. Put a 2 there. I get a negative 4. Put a negative 8 there. I get a 4. And I put an 8 there, and I get a 0. Ta-ta-da-da. Now this becomes x squared, and that's an x, and that's a constant. So I'm whittling this down. Once you get it down to a quadratic, you should be able to unfoil it, and if it doesn't unfoil, then you can use quadratic formula. So I have x minus 2 twice, and then lo and behold, this actually is another perfect square, so it ends up being x minus 2 times x minus 2 4 times. So this is a perfect fourth root. This was x minus 2 to the 4th power, so the solution here is 2 with a multiplicity of 4. And that makes sense because the multiplicity was even and even multiplicities don't pass through, they bounce back. You know what I'm saying? Yeah.
But for the other one, like when it was like the 3, wasn't there like 4x minus 3s and you said multiplicity of 3? No, you said multiplicity
No.
of 4, but the answer is 3.
Yeah. It was, the answer was 3, but there was, wait, what? I don't remember what it was. You'll have to rewind on the video. Okay. What else do we have on the next page here? We're getting to the 20-minute mark. Irrational root theorem we'll cover tomorrow.
Welcome to our TED Talk.
Here is an example just I clipped out from the book. This just highlights everything from start to finish again. So, you know, getting used to reading the book. Look at how obnoxious this one is because it has a leading coefficient that's 4. And so what happens now is you'd have a Q value where all those are possible roots, and then you have a P that's a -6, so you'd have all those that are possible, and then you get all of these, including those fractions. Holy cripes. So now you have all those, which ends up being like 16 different possibilities if you just had to guess and check. That's why they used some technology to graph it, and they determined that 2 was one of them. So they used 2 in the rational root theorem and the synthetic division to determine the first factor was x minus 2. Then they had this leftover stuff here, and the leftover stuff they did synthetic division again with what appeared to be -3/4. So they went -3/4 right there, which, yeah, you can put a fraction in there in synthetic division, and they ended up going like that, and they ended up getting it down to a quadratic. So now we determined that x minus 2 is a factor, and x plus 3/4 is a factor, and now we got this quadratic left, which DNF'd, did not factor. So if it DNF'd, then they QF'd it on it, and so now we have the UQF, and they ended up with some irrational roots, 2 plus or minus the square root of 3. Okay? Yeah. Yep. Yeah. Use Desmos as a graphing calculator app in self-service, or some sort of whatever graphing calculator you have. But in this one, then the four roots were 2, -3/4, and then 2 plus root 3 and 2 minus root 3. And so what the irrational root theorem essentially says, if you read this, for every polynomial p of x, blah, 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 it basically says that irrational roots come in pairs, right? Because how do you get an irrational root? You get it from like quadratic formula or square root both sides, which has a plus or minus element to it. So irrational roots come in pairs. Okay? All right, I'm going to stop there for today. And yeah, we're not in Kansas anymore.